Gravity is weird. Of all the forces that run the universe, it's the odd one out. It feels strong to us. It holds us to the Earth. It keeps the moon in orbit. It holds the sun and all its planets together. It gathers galaxies into massive clusters. On a cosmic scale, gravity is the boss. But in reality, it's shockingly, embarrassingly weak. Think about it. You can pick up a paper clip with a tiny refrigerator magnet. That little magnet with its electromagnetic force is easily overpowering the gravitational pull of the entire planet Earth. The whole planet, all 6 sextillion tons of it, is pulling on that paperclip, and a flimsy piece of magnetized metal wins. This isn't just a party trick, it's one of the biggest mysteries in physics. It's called the hierarchy problem. Why is gravity so much weaker than the other fundamental forces? The strong nuclear force, which binds atomic nuclei together, is immensely powerful. The electromagnetic force, which governs light and magnetism, is a titan. The weak nuclear force, responsible for radioactive decay, is still trillions and trillions of times stronger than gravity. And gravity is the runt of the litter. By a lot, not just a little bit weaker. We're talking about a difference so vast it's hard to put into words. If the strong force was the strength of a grizzly bear, gravity would be the strength of a single tired ant. For decades, physicists have been trying to figure out why. Why this huge gap? Why is our universe built this way? The standard model of particle physics, our best description of the universe at the smallest scales, works incredibly well. But it doesn't include gravity, and it doesn't explain this weakness. It just states that this is how things are. You plug in the numbers and they work. But it doesn't say why the numbers are what they are. And this is where the really wild ideas start. What if gravity isn't actually weak? What if it's just as strong as the other forces, but we're only feeling a tiny fraction of it? What if the rest of it is going somewhere else? Somewhere we can't see? What if gravity is leaking? It's leaking from our dimension into another one. This sounds like science fiction, and for a long time, that's all it was. And extra dimensions were the stuff of pulp novels and late-night movies, but in theoretical physics, the idea has been around for a surprisingly long time. It wasn't just a crazy fantasy, it was a serious attempt to solve deep problems in our understanding of the universe. The story starts about 100 years ago. Einstein had just turned physics on its head with his theory of general relativity. He showed that gravity wasn't a force in the traditional sense, it was the curvature of space-time itself. Massive objects warp the fabric of reality, and other objects follow those curves. It was a beautiful, elegant theory. It worked perfectly. Around the same time, another force, electromagnetism, was also well understood. A physicist named Theodore Kaluza had a radical thought. What if you could unite Einstein's theory of gravity with the theory of electromagnetism? What if they were two sides of the same coin? He tried to do it using the standard 4 dimensions. We know 3 of space length, width, height, and 1 of time. It didn't work, so he tried something strange. He added a 5th dimension to Einstein's equations, just to see what would happen. And when he did, something magical occurred. Out of the math, not only did he get general relativity back, but he also got the equations for electromagnetism. Well, they just appeared. It seemed that in a 5-dimensional universe, gravity and electromagnetism were unified. They were part of the same single entity. But this raised an obvious question. If there's a 5th dimension, where is it? We certainly don't see it. We can move forward and backward, left and right, up and down. But we can't move in some other force-spatial direction. A few years later, another physicist named Oscar Klein came up with a possible answer. He suggested that the 5th dimension is there, but it's curled up. It's rolled into a tiny, tiny circle, so small that we can't perceive it. Imagine a garden hose. From far away, it looks like a one-dimensional line. It only has length. But if you get very close, you see it has a second dimension, the circular part you can go around. Klein proposed that the extra dimension of space was like that. At every single point in our familiar space, there's a tiny, curled-up circle of another dimension. It's too small for us to ever enter or even detect. This idea, called Kaluza-Klein theory, was brilliant. But it had problems. It didn't quite match all the details of the real world, and soon, 2 new forces were discovered, the strong and weak nuclear forces. The simple 5-dimensional picture couldn't account for them. The idea of extra dimensions faded into the background for a while. It was a neat mathematical trick, but it didn't seem to be the answer. Then came string theory. In the latter half of the 20th century, physicists were trying to solve the biggest problem of all: how to unite general relativity, the world of the very large, with quantum mechanics, the world of the very small. The 2 theories are masterpieces, but they don't play well together. They speak different languages. String theory was an attempt to be the translator. The basic idea of string theory is that the fundamental building blocks of the universe aren't point-like particles. They're tiny, vibrating strings of energy. A string vibrating in one way might look like an electron to us. The same string vibrating in a different way would look like a photon, and another vibration would look like a quark. All the particles and forces we see are just different notes played on these fundamental strings. It's an incredibly ambitious and elegant idea, a potential theory of everything. But it came with a very strange requirement. For the math of string theory to work, the universe couldn't have just 3 spatial dimensions. It needed more, a lot more. Depending on the version of the theory, it needed 9 or 10 spatial dimensions plus 1 of time. And so, extra dimensions were back. They weren't just a clever trick anymore, they were a core requirement of our best candidate for a theory of everything. But the old question remained. If these extra dimensions exist, where are they? The Kaluza-Klein idea was still on the table. Maybe they are all curled up, incredibly small, so small that we have no hope of ever seeing them directly. This was the standard answer for a long time. The extra dimensions were a mathematical necessity for the theory, but they were hidden away at a scale so tiny they had no real effect on our everyday lives. Then, in the late 1990s, a few physicists had a different idea, a much bolder idea. What if the extra dimensions weren't all microscopic? What if some of them were actually large? This new idea came from a concept in string theory called branes. The word is short for membranes. The idea is that our entire 3-dimensional universe might be a brane living inside a higher dimensional space called the bulk. Picture it this way. Imagine a vast, empty swimming pool. That's the bulk. Now imagine the surface of the water in that pool. That surface is a 2-dimensional world. Any creature that lived only on that surface would think the universe was 2-dimensional. They could move forward and backward, left and right, but they wouldn't know about up and down. They'd be stuck to the surface. The brane world idea is that we are like those creatures on the surface. Our universe, with its 3 dimensions of space, is a brane. This brane is floating in a larger, higher dimensional bulk. There could be 4, 5, or even more spatial dimensions in the bulk. This is where it gets interesting. According to this idea, most of the fundamental particles and forces are stuck to our brane. The particles that make up you, me, the Earth, and the stars, electrons, quarks, are all like open-ended strings. And the ends of these strings are anchored to our 3D brane. They can't leave. The strong force, the weak force, and the electromagnetic force are also transmitted by particles that are stuck on the brane. They are, for all intents and purposes, purely 3-dimensional phenomena, but gravity is different. In string theory, gravity is caused by closed loops of string. These are called gravitons. Because they are closed loops, they don't have open ends that need to be anchored to the brane. They are free to travel anywhere. They can leave our brane and float off into the bulk. And that provides a stunningly simple explanation for the hierarchy problem. Gravity isn't weak. It's just diluted. The reason gravity seems so feeble to us is that its influence is spread out across all the dimensions, both our 3 and the extra ones in the bulk. The other forces are concentrated here, on our brane, so they feel strong, but gravity's strength leaks out into the vastness of the extra dimensions. What we feel here, in our little corner of reality, is just a tiny whisper of its true power. It's like dropping a pebble in a pond. The ripples spread out in 2 dimensions on the surface, and they get weaker as they go. Now imagine you could make a sound in a huge 3-dimensional concert hall. The sound waves spread out in all 3 dimensions. It'll get weaker much faster. The brane world idea is that gravity is spreading its influence out in more dimensions than the other forces. This specific model, proposed by physicists Nima Arkani-Hamed, Savas Dimopoulos, and Gia Diwali, is often called the ADD model. It suggested that these extra dimensions could be surprisingly large, not curled up at some impossibly small scale, but perhaps as large as a millimeter. You might ask, if there's a dimension a millimeter wide, why can't we see it? Why don't we just fall into it? The answer is that we can't. We and all the matter we're made of are stuck to the brane. We can't move in that extra direction any more than a cartoon character drawn on a piece of paper can lift himself off the page. Only gravity can travel there. But how could we test such a wild idea? You can't just build a probe to explore another dimension. But there might be indirect ways. The ADD model makes a fascinating prediction. It says that gravity only appears weak at the large distances we're used to. At very, very small distances comparable to the size of the extra dimension's gravity should get much, much stronger. As you get closer to another particle, less of the gravitational force has had a chance to leak away into the bulk. So, if you could do experiments at incredibly small scales, you should see gravity suddenly become as strong as the other forces. This led to a blockbuster prediction for particle accelerators like the Large Hadron Collider LHC at CERN. The LHC smashes protons together at nearly the speed of light, creating immense concentrations of energy in tiny spaces. One of the worries people sometimes have about the LHC is that it could create a black hole that would swallow the Earth. Physicists always said this was impossible because the energy needed to squeeze matter into a black hole is astronomical, far beyond what the LHC could ever produce. But that calculation was based on our normal, weak 3D gravity. If the brane world idea is correct and gravity gets much stronger at tiny distances, then the energy needed to create a black hole is much, much lower. It might be low enough for the LHC to do it. So one way to test this theory is to smash particles together and look for the creation of microscopic black holes. These wouldn't be the planet-eating kind. They would be unimaginably small and would evaporate almost instantly, in a fraction of a second, through a process called Hawking radiation. They would decay into a spray of ordinary particles in a very specific, recognizable pattern. If scientists at the LHC saw this signature, it would be earth-shattering evidence that gravity is leaking into large extra dimensions. There's another way to look for evidence. If gravitons can leak off our brane, then maybe we can create them and watch them disappear. In a high-energy particle collision, some of the energy could be converted into a graviton. This graviton, not being stuck to our brane, would zip off into the bulk. We wouldn't be able to see it directly. But we could infer its existence. Physicists are very good at accounting. They measure all the energy and momentum of the particles that go into a collision, and they measure all the energy and momentum of everything that comes out. The two should match perfectly. It's a fundamental law of physics: energy is conserved. But if a graviton is created and escapes into the bulk, it would carry energy and momentum with it. When the scientists tallied up the results, the numbers wouldn't add up. There would be energy missing. This missing energy would be a telltale sign that something invisible had been produced and had fled the scene of the crime, escaping into another dimension. So, scientists at the LHC have been looking. They've been searching for mini black holes. They've been searching for events with missing energy that can't be explained by other more mundane particles like neutrinos. And so far, they've found nothing. There has been no sign of microscopic black holes. No definitive evidence of energy leaking off our brane. This is a bit of a disappointment for proponents of the theory. The simplest versions of the ADD model, the ones that predicted these effects would be easily visible at the LHC, have been ruled out. But that doesn't mean the whole idea is wrong. It could just mean that the extra dimensions are smaller than we thought. Maybe they're not millimeter-sized, but much smaller. Small enough that the LHC doesn't have quite enough energy to probe them. The effects could be there, just waiting for a more powerful collider to uncover them. There's also another slightly different version of the brane world idea called the Randall-Sundrum model. Proposed by Lisa Randall and Raman Sundrum, this model also uses branes and an extra dimension, but it works a bit differently. In their model, the extra dimension doesn't have to be large. It can even be infinitely big, but it's warped. Space-time is curved in a very particular way. In this scenario, there are two branes. One is our brane, where we live. Let's call it the weak brane. A little far away, across the warped extra dimension, is another brane, the gravity brane. In this setup, gravity is naturally very strong on the gravity brane, but because of the way the dimension is warped, its influence gets exponentially weaker as it travels across the bulk to our brane. So we, on the weak brane, feel only a faint, diluted version of it. The hierarchy problem is solved not by gravity's force spreading out over a large volume, but by our being located at a position in the extra dimension where gravity is naturally suppressed. This model is also testable at the LHC. It predicts the existence of new heavy particles that are related to the graviton. These particles, called Kaluza-Klein gravitons, are essentially echoes of the graviton in the extra dimension. If they exist, they could be produced in high-energy collisions and then decay into particles we can detect. Again, scientists have searched for these particles, and again, they have so far come up empty. So where does that leave us? Is gravity leaking from another dimension? The honest answer is we don't know. It remains one of the most exciting and tantalizing ideas in modern physics. It's a beautiful, compelling solution to a very deep puzzle. But, as of now, it's an idea without evidence. The lack of evidence from the LHC has certainly dampened some of the initial excitement. But science is a long game. The absence of evidence isn't necessarily evidence of absence. It could just mean we're not looking in the right place, or with powerful enough tools. But it's worth thinking about what it would mean if it were true. It would fundamentally change our picture of the universe and our place in it. Our reality would not be the whole story. It would be just a thin slice, a membrane, in a much larger, more complex cosmos. It raises all sorts of mind-bending questions. Could there be other branes, other universes floating parallel to our own, just a short distance away in another dimension? This idea offers a potential explanation for another huge cosmic mystery, dark matter. About 85% of the matter in the universe is dark. We can't see it. It doesn't interact with light. But we know it's there because we can see its gravitational effects. It's what keeps galaxies from flying apart. We have no idea what it is, but what if dark matter is simply normal matter, made of familiar particles like protons and electrons, but it exists on another brane, parallel to ours? If that were the case, we would never be able to see it or touch it, because the forces that allow for seeing and touching are stuck on its brane, just as ours are stuck on ours. But we would be able to feel its gravity, because gravity is the one force that can travel between the branes. This parallel world would be invisible to us, yet its gravitational pull would shape our own cosmos. It's a wild idea, but it's an elegant one. The implications go on. Some have even suggested that the expansion of the universe and the mysterious dark energy that seems to be driving it could be caused by interactions between branes. Maybe our brane is being pulled by another, or maybe two branes collided in the distant past, an event that we perceive as the Big Bang. These are just speculations. They are what physicists think about when they're pushing the boundaries of what we know. The idea of gravity leaking into other dimensions might ultimately turn out to be wrong. Science is full of beautiful ideas that don't survive contact with reality. That's how the process works. You come up with a creative solution to a problem, you figure out how to test it, and then you let nature tell you if you're right. For now, nature has remained silent on the subject. The LHC has given us the Higgs boson, completing the Standard Model, but it hasn't opened a window into another dimension. Not yet, anyway. But the problem that started it all hasn't gone away. Gravity is still ridiculously weak, and we still don't know why. The hierarchy problem is a constant thorn in the side of physics. It tells us that our understanding is incomplete. There's something big we're missing. Maybe the answer is something else entirely. Maybe it's a different theory like supersymmetry, which proposes that every known particle has a superpartner that we haven't discovered yet. The interactions of these undiscovered particles could, in theory, stabilize the hierarchy and explain gravity's weakness. Or maybe the answer is something no one has even thought of yet. But the idea of leaking gravity in extra dimensions refuses to die because it is so compelling. It takes a frustrating flaw in the universe, the absurd weakness of gravity, and turns it into a clue. A hint that reality is vastly larger and stranger than it appears. It suggests that the world we see is just a shadow of a higher dimensional reality. It's a humbling thought. We look out at the night sky, at the vastness of space, and feel small. But maybe the three dimensions we see are themselves just a small part of a much grander stage. Maybe the reason gravity feels so weak is because it's the only force that knows about the rest of the show. It's the only thing that connects our sliver of a world to the true, deep reality of the bulk. We don't know the answer. We might not find it in our lifetimes. But the question is, what matters? Why is the universe the way it is? And in the search for an answer, even an idea as strange as gravity leaking into another dimension is worth taking seriously. Because sometimes the strangest ideas are the ones that turn out to be true.